Alright, so welcome back. This video is about taking everything we've learned so far and smooshing it into this final idea of how to actually do oxidation reduction reactions. And to do that, we're going to need to learn one more concept. And I promise it's not too bad. At the end of this, we can look at a couple reaction videos and see these things kind of, instead of just being note cards, as, well, chemistry. And it allows us to bring all of what we've been learning together. And to be clear, we are getting closer towards the finish line for this chapter. This is the last concept of this part, and it's going to take us into the last thing we do in chemistry, which we'll actually transition into today. So this is getting somewhere, even if it has felt like we've been doing oxidation numbers and oxidation reductions for so long. Really, we're getting where we're supposed to be. So let's start off by looking at a pretty straightforward reaction and using it as some review. And that is the reaction between potassium and bromine to make potassium bromide. So the first thing we're going to need to do is write oxidation numbers for this thing. Now, potassium and bromine, they're elements all by themselves. So what are their oxidation numbers? Right, so they're both 0, and any element by themselves is 0. And for that matter, KBr as a group here is 0. There's no charge written here to the side, right? Now, let's take a look at this one. We need to break it into its two different ions, its two different oxidation states. And we know something about K. Potassium always has what charge in a compound, what oxidation state, because it's a 1A metal. By extension, of course, if this thing needs to add up to 0, and this is a +1, this has to be a -1. All right, so let's identify the oxidation and reduction happening here. Right, we're going to draw a line connecting each like element, potassium to potassium, bromine to bromine. And let's ask, what's happening to bromine in this reaction? Is it being oxidized or reduced? All right, so the number went down, which means it gained electrons, so it's reduced, not oxidized as I tried to write. And potassium is being oxidized. Pretty straightforward. Up until this point, this is the part I care most about, right? If I can give you a chemical reaction, have you do this. If you can take a thing, and give me its oxidation numbers, and identify what's being oxidized or reduced, you'll walk out of Rockhurst being able to say, hey, I did redox chemistry. But in real life, you're not going to come across these words nearly as often as one other thing. So this is the curveball, and I will admit it's a little confusing. And the best way to do it is just to kind of plow through it for a minute. So if you don't have something to write down with your notes or something, this would be a good time to pause me and grab a piece of paper and just write down a couple notes. Occasionally on something you buy at like a hardware store, you'll see this NFPA triangle, or diamond I suppose, with kind of like a face that looks like it's on fire. And that's the symbol for an oxidizer or oxidizing agent. Oxidizing agent is the thing that's being reduced. Think of it as like the chemical that actually lets the oxidation happen. This is the reactant that's actually gaining the electrons. But this bothers me because it's called the oxidizing agent, but it's undergoing reduction. Right? Shouldn't it be the other way? Shouldn't we call this the reducing agent just by these two logical things? And this does bite students in the butt. So it's good to remember that the agent is the opposite of what you expect. If you have to think about someone like being an undercover agent who is a spy or something, that works. So the thing that actually allows the reaction to undergo oxidation is the thing that's being reduced. So the thing being reduced we call the oxidizer. Now, oxidizers are actually really important to identify in real life, and they're quite often dangerous. Now, I'll demonstrate that for you in just a moment. So that's what you'd actually need to know, is like, hey, if this is an oxidizer, it's probably relatively dangerous, especially around fires. Now, oxidizing agents have a partner, and their partner is the reducing agent, which is the thing being oxidized. And again, it's this opposite that you wouldn't necessarily think about. It's really important to look at only the reactants of the reaction for this part, only the things at the beginning of the arrow, right? And for this to work, you'd have to like find the oxidation states, those numbers along the top, right? And the oxidation reduction to actually be able to identify, hey, which thing's the reducing agent, which thing's the oxidizing agent. And yeah, those things are tricky. Let me get these things organized for you. So let's look back at this reaction for a moment. Again, potassium and bromine react to make potassium bromide, where potassium undergoes oxidation and bromine undergoes reduction. We talk about what happens based on the reactants, right? Potassium undergoes oxidation. So while we're here, is potassium the reducing agent or the oxidizing agent? You may need to look at the top here for a quick hint. Alright, so a little tricky, right? Potassium undergoes oxidation, and because it's being oxidized, because it's undergoing oxidation, it's the reducing agent. And bromine is the oxidizing agent, and I understand that my colors are backwards here. I just noticed that. I apologize. But that's tricky. And yeah, in the scheme of things, I much more care about the numbers and being able to connect them over like being able to identify these agents. But once you have oxidation, the product side of oxidation does not matter, and the reactant side of oxidation is called the reducing agent. Once you have reduction, the product side does not matter, and the reactant side is going to be called the oxidizer. So let me clean this up, and let's take a look at a more complicated reaction. All right, I know this is a little intimidating looking, but it's not so bad. We have sugar reacting with a thing called potassium chlorate to make familiar things. Potassium chloride, water, carbon dioxide. And I haven't filled in all the oxidation numbers. I've just really highlighted the two things that really matter in this reaction, which is the carbon and the chlorine. So before we go any farther, what's happening to the chlorine in this reaction? Is this oxidation or reduction? So, knowing that this is undergoing oxidation and this is undergoing reduction, is the sugar the reducing agent, or is the potassium chlorate the reducing agent? I want to point out again that we're only really looking at the stuff at the beginning, before the arrow. Right? The stuff back here matters only insofar as it helps us identify these. But the agents are all there at the beginning. Now, sugar was oxidized, so it's the reducing agent. Potassium chlorate, well, it was reduced, so it's the oxidizing agent. And actually, potassium chlorate here is a really powerful oxidizer. This is partly because it actually breaks into pure oxygen, and then that oxygen goes on to react with the fuel, with the reducing agent. And so once the reaction kind of gets going, it self-feeds itself, and it's like giving it pure oxygen. It makes it really useful in like simple rocket fuels, pyrotechnics, things like that. That's also why it's a relatively hard chemical to get your hands on. Obviously, we have a decent amount of it at Rockhurst. But it is a more dangerous chemical, and I'm going to show you a favorite demonstration of this, which is where you take some sugar in the form of a Haribo gummy bear and react it with some molten potassium chlorate. Now, I'm not going to show you me filming this in the lab because I didn't think to film it before we were in quarantine. So I went on YouTube and I found someone else doing this reaction. It's really common, and I don't particularly like his technique, but the video looks very good. So let's go over to that really fast. So you'll see the molten chlorate at the bottom, and then he mixes it with the gummy bear, and in it goes. It's a quite energetic reaction. One of the things I don't like is that he did this outside of a fume hood. Not particularly smart. And actually on YouTube there's a lot of people who've run this reaction in the open like this, which I really don't care for. Lots of things could go wrong there. One thing I want you to think about is that the potassium chlorate really only sped this reaction up. But in a lot of ways, the energy in this reaction is very similar to what happens in your body, albeit in a much faster way. Your body's very slow when you eat a gummy bear. The energy in this reaction, the energy in one little gummy bear is actually pretty incredible. Right? That's a visual representation of the calories available in one little measly gummy bear, let alone a whole bag. But there's a way to actually show you what this would look like, right? What happens when you do react a lot of gummy bear with some chlorate? What if you had a giant gummy bear and tried this? Again, I'm going to use someone else's video because we tried this once at Rockhurst, and Mr. Doyle might have burned the parking lot a little bit, and we were afraid of having the fire department show up, and it's better to watch a video of it. So let's go back over to that. I've paused it here for just a second, and you can see these gummy bears are quite a bit larger. Now, the one we used at Rockhurst was another order of magnitude larger, about 5 pounds. These look like they're maybe, I don't know, a couple 100 grams at most. And there's some molten chlorate in the bottom of those beakers on top of that poor hot plate that's about to have not a great day. And they're going to drop the gummy bears in.
Oh, go.
One of the things I want you to notice is the two different colors here. And that's actually coming because there's two different kinds of chlorate being used. The purple's potassium chloride, and the bright yellow that's kind of outliving it was sodium chloride.
Why is it on fire?
I mean, it's actually not that hard of a question. It's on fire because you just dropped a lot of stuff in potassium chlorate, and that's kind of what happens. And they even chose to document how stupid they were by doing this outside of a fume hood. Fantastic. Oh, and look at that lovely mess to clean up, too. Nice. So let's do another problem from start to finish. Your homework tomorrow looks a lot like this, and I think it's good to have some practice with it. We're going to use the familiar thermite reaction because you've seen it, and I really like it. And it gets the point across while doing some of the more difficult parts of this. All right, so the first thing we need to do is find the oxidation numbers. Because aluminum and iron here by themselves, they're 0. Great. But let's look at something harder, this iron oxide here. Now, you know the charge on each oxygen atom. This isn't a peroxide. So what would each oxygen be worth in this reaction? Great, so this group here of oxygen, this whole thing is worth -6, right? I've got 3, each worth -2, so this Fe group has to be +6. But what does each atom of iron have to be in this compound? While we're here, aluminum oxide ends up working out exactly the same, kind of conveniently. And this lets us connect the things that matter and say what's happening. So right off the bat, I notice that oxygen doesn't change oxidation states. So what is its role in this reaction? All right, so the rest of them come together nicely. Oxidation reduction should be old hat for you by now. So which thing is let's go with oxidizer in this reaction. Which thing here is causing the oxidation? All right, so this thing here was undergoing oxidation, right? The number went up. It was losing electrons. Because it's losing electrons, it's allowing something else to take electrons in, making it the reduction agent. The iron here, it wants to gain electrons. So because it can allow something else to lose electrons, we call it the oxidizer or the oxidation agent. The easiest way to think about this is oxidation agents come from the reduction line. Reduction agents come from the oxidation line. Now, with all this written out, we could write some half reactions if we really wanted to do that. And that would work pretty well. But there's a different problem too. Sometimes you want a reaction to happen and it just won't. And you can try like pointing a wand at it, but I've personally not had a whole lot of luck doing that. But there is a way to force oxidation reactions to happen that maybe wouldn't otherwise. And yeah, I'm not a teacher at Hogwarts, so this isn't going to work. But I'm going to show you a picture of the setup we're about to use to make a reaction happen by forcing oxidation reduction without using chemicals. We're only going to use one ingredient, as a matter of fact. And that ingredient is just tin 2 chloride, stannous chloride. Now, you might notice it's got all kinds of interesting side effects. Severe irritation to the upper respiratory tract, not good at the moment. Vomiting, watery or bloody diarrhea, collapse and collisions, liver and kidney damage. Not the most fun thing to just like have on your desk, but in the same breath, don't eat it and you'll be okay. So we're going to use this chemical, and we're going to make some chemistry happen here in a new way. And that reaction should help us understand where we're going next right after Easter. All right, so let's cut over to a picture of my desk right now. So it's a bit messy, but that's because I don't have a chemistry lab. And you can see we're going to film something going on in that petri dish at the bottom. Now, one thing to really notice is the thing with the red display in the background. That's called a power supply. And that's the trick for what we're doing today. We're going to use electricity to make a chemical reaction happen. So we're going to get an arbitrary amount of tin 2 chloride. And that's just going to be a couple grams here. Just a healthy shake kind of thing. You'll notice the first thing that comes out here is a big crystal. Not particularly useful to us, but that's life. And all crystals, right? So we'll need a way of grinding those up, which I don't particularly have. So instead, we're going to have to wait and let the water do it for us. And water will be mixing in this very not orange juice, and we'll just mix it in and shake it up. All right, you might notice I'm using the filter paper here to do this. That's kind of a trick. That way, if I have any left over, it won't end up in my product. And as I dissolve these, you'll notice it's turning very milky white. That's very normal for tin 2 chloride. It is quite soluble, but it leaves behind this cloudy precipitate, even in distilled water, which this obviously wasn't. That being said, we're going to need to filter it. So let me set it up after I finish shaking this and show you what that looks like. All right, so you can see the setup I'm running right now. That's a simple filtration. I have an Erlenmeyer flask here with a funnel and some coffee filter, and I'm just pouring it through. You'll notice it's both slow and relatively inefficient, right? This is taking a long time, and it's still white once it comes through. So you have to run this a couple times, unfortunately, and it's going to take a while. So I'm not going to show you all that. It will take, 30 minutes for this to all pass through a few times. So be back once that's done. All right, so I've got this thing set up right now, and in that other picture you just saw, you can see it's a little bit wider than this, but I have a black and a red wire, a negative and a positive. And these are going to end up working as a source and a sink for electrons. In other words, this thing is going to give electrons off, and this one's going to take it. And I'm going to do that by forcing electricity through. So the electricity is going to flow, well, from red to black, but the electrons flow from here to here, right? So we could actually draw that in really quickly. So what's going to happen is, in this petri dish, the electrons are going to go from here to here. Now, I spent like 2+ hours letting this thing filter, and you can see it's nice and clear now. And so I'm going to add this liquid, which is tin 2 chloride, to the petri dish here. And just try to give it as little of that white as possible. I still need to let it cover the whole bottom. I think that's probably enough. We'll see. Yeah, that's good. All right, so these little paper clips are acting as what are called electrodes, as contact points, and they have to be in the water, obviously, otherwise it's not going to work. And I'm going to put electricity through it. And it's not going to be particularly fast, but let's go ahead and start that. You can see right off the bat, there are bubbles forming on the black one, which means I have an electrical circuit running through here, so the electrons are doing it. And I think I'm just going to let this thing run as a time lapse for a while. Alright, so I want to talk briefly about what's actually happening here. Obviously there's two different products in here. The first is this light white solution here, and this is tin 4 chloride. Remembering the clear stuff is tin 2 chloride. And then the gray stuff here is actually tin metal in a spongy form. Now, about halfway through, I added this paper clip, and what it's doing is it's acting as a little wire, basically. And it's acting as a microcosm. So this end is going to be just acting like this red, and the black is acting like that. And anytime you would add a new wire in here, it would begin to react that way. So you can see these are getting pretty close together, and nothing really special happens when they meet. So that's one thing. But I actually want to move these around a little bit. So the first thing I do is I'm going to remove this red. And then I'm going to move this. And you already notice the sponge is a little bit loose there. But if I bring them close together, obviously the reaction's a lot faster. And as I pull them apart, the reaction slows down a little bit. Right? I don't know if you can kind of see the difference in that reaction rate. So the closer these things are together, the faster that reaction is going to go. And that's because the electrons don't have to travel as far through the liquids. There's a more direct path from plus to minus. There's a easier flow from the sink to the drain. Now, the reason why I spread them out so far is it's kind of cool to see the crystals grow over time, and you can at least see what's happening. Here it's just foamy. If I do pull them apart, you can see there's new tin that's formed here, and of course a little white splotch of the tin 4 chloride. And in the same thing, if I were to short this here carefully, the reaction is going to proceed so quickly that it basically clouds what we can see. So it's neat to see this, but being really clear, this isn't the best setup. I'm at home. I had a lot of trouble getting things to filter. My chemical's a little old. And so I want to watch this video in the purest, best way. Someone who has access to tin and strong acids to make brand new solutions right now. And kind of see what this could look like in its best form. And then come back to a still picture that you might have just seen me take here in a second, and actually talk about what's really going on in this reaction. So this is from a YouTuber, Nile Red, and the setup is almost identical, except his chemical here is a little more pure. He's dissolved tin directly into hydrochloric acid to make the tin 2 chloride, so it's very fresh. And it makes a very different looking reaction. He's hooked it up to a similarly powerful power supply, and his electrodes are a similar-ish distance apart. Mine were a little farther. But you'll notice the reaction is pretty wildly different. So the little fingers forming here are dendrites. Those are tin metal, just like my tin sponge was. And why they're forming differently, I don't have a great answer. But even more confusingly is that the tin 4 chloride directly goes into solution instead of making a white film. Right? Remember, mine had that milky precipitate around it. So my hunch here is that my chemicals are impure, because this reaction here is more what I'm used to. So let's come back here and look at a picture of the final product. And again, I want to talk about the fact that we have tin and tin 4 chloride both coming from the same reaction. So let's take a look at those two reactions split apart into half reactions really fast. So I've written the two reactions that are happening by the black and red electrodes here. And let's take a moment and identify which thing is the reduction reaction. Is it the one by the black clip or the one by the red clip? So what I think is so neat here is that only using electricity, and only using electricity, we're getting two different reactions to happen. We're getting the reduction and the oxidation just because we're moving an electron. Now, that's really neat. And finishing things off here with one more time lapse from now, red. It may not be obvious to you just yet, but what we're doing right now is actually establishing a really important link between chemistry and electricity. See, electricity can be used to make a chemical reaction happen, or chemistry can be used to create electricity, a process with which you are actually quite familiar already. You just have never thought of it that way. So that's where we're heading. What's the link between electricity and chemistry? For tonight, you're done. Nothing more. Thanks for your time. I hope you have a great day. Be gentle to each other. Y buen camino.